Hello! Welcome to my Graphics 2 course summary. In this course, students build a software rasterizer. So I'm going to break down all the progressions to end up with a filled triangle Phong shaded scene. So this course is the next in line after my Graphics 1 course. You can find a link to that course summary in the description. And I like to think it ties really nicely into the previous course. So what we actually do is we take what we do in the first couple weeks of Graphics 1 in ShaderToy and we port it to a C++ software renderer. So the simplest possible shader is just filling the entire image with a solid color. So students understand at this point that for, in this case, all 1075 by 604 pixels in our image, we evaluate the equation defined by our fragment shader, but now we go one step further by actually having to write the nested for loop responsible for writing said color to our frame buffer. So we start with that, and then we just kind of keep the progression going. So we have filled color, then we have gradients, 1D, 2D, and then I can even challenge students to make something like an SDF, filled SDF. So for example, usually students hit a little bit of a wall typing step into C++ and wondering why they have a compiler error. And I say, well, this is a different language than GLSL, so in order to fill in the blanks, you need to read the GLSL documentation and port the step function accordingly. And from there, depending on how much a challenge students are looking for, we can even port some fractals to C++, so they have to recreate fract for domain repetition. So there's the fract function. It's a very simple equation, just getting students in the habit to dive one level deeper. And once they have that complete, they can go as far as making the final fractal we make at the first half of Graphics 1. So here we go, we've got a solid color, then we have a 2D gradient, so we can see the code right here. Given the new information, instead of frag chord and I resolution, I have this global constant CPU image size, so students have to figure out that, hey, we need to take our current pixel position and divide it by the resolution of our image to get our UVs, to write a gradient accordingly. And now here's where it gets interesting. So I don't require students to write the circle SDF just for fun. It actually poses a really interesting problem. So if we get our FPS counter back, we can watch our frame rate nearly cut in half when we render a circle distance field. So I say to students, okay, this is not really an acceptable frame rate, especially for rendering a single object. So how can we speed up rendering a circle? And that introduces rasterization in the form of Bressenham's circle drawing algorithm. So we go from this distance field and then again, maybe, steps right into there. No need for a filled circle. Just do a quick and dirty SDF. So now we set up some rasterization. So one graded exercise I like to do is I give students some function signatures and they fill in the blanks. So they have to make a function that draws a horizontal line, a vertical line. I give them some pseudocode for the DDA algorithm that draws a line in an arbitrary direction, and then a rectangle that's filled, outline of a rectangle, there's Bressenham's circle drawing algorithm, and then the outline of a circle. So lots of very simple 2D primitives, and then there's some engine integration. For example, draw a line from the center of a circle to the mouse position, and they have lots of fun playing with objects in screen space. So this is the demo for that. Everything is in line. They just have to overload an update function and potentially a load and unload function for later demos that will load images and meshes. So they don't even need to really know the nuts and bolts of C++. I'd say this is very similar to the processing Java framework, where you kind of just write the logic and the engine will take care of the rest. So there we go, we've introduced rasterization. So now let's open the floodgates. Time for some geometry. So I start off by making our GPU's best friend the simplest possible 3D shape. We have our triangle, and from there I also introduce the concept of triangulation, where if we're trying to specify a plane without duplicating any vertices, the layout looks like this. But if we assume our GPU only knows how to render a triangle, we have to triangulate, so going from a set of unique vertices to a set of triangles. And I learned by writing OpenGL, of course, and the concept of an index buffer is pretty intuitive in English, but it still solidified it even more when I wrote this simple algorithm manually. So I find this is a really good way to instill fundamentals to students. So we've got a triangle. It doesn't need an index buffer because its vertices are by definition its indices. Then we can triangulate our plane. And lastly, unfortunately, the internal call looks a little bit different, but just for some wow factor, I get my engine to load a mesh. I extract just its vertex positions. Of course, it's complete with a lot more than just vertex positions, but we introduce that later. And we can render a sphere's wireframe in screen space. So if we look at the actual rendering code, again, based on how much of a challenge you like, you can either fill this function in entirely, or you can say, okay, guys, well, before we were defining pixels from 0 to the resolution of our image, but if you look at our vertex data, it's in the range of -1 to 1. So what gives? So that sort of intuitively sets up device coordinates versus screen space. And again, I can say, hey, look at the scalar functions defined at the top of our math library, which is Raylib's math library, basically. Excellent library, much better than GLM. So yeah, they transpose from device coordinates to screen space and then call their earlier DDA line drawing algorithm. So there we go. We can either render a single face. We're manually rendering a plane here because it's 2 triangles, and then for obviously larger collections of triangles, we can just use a for loop to draw the current triangle as a wireframe. So that introduces geometry and position buffers, vertex buffers, whatever you want to call it. So now time to add matrix transformation. So we can rotate our triangle in device coordinates, rotate our plane, rotate our sphere, rotate any geometry of your choice. And again, in Graphics 1, students should be very familiar with the concept of matrix transformations. It's just now, applying them a little bit more manually, where we say for every vertex in our mesh, in order to apply our transformation, the new vertex is equal to the old vertex times our transformation matrix. So we take that and we must be careful to make a copy of the original vertices, otherwise we'll end up in a feedback loop and our transformation will escape out of control. So sometimes students will deform the original mesh over and over and they get a crazy looking transformation, so that ends up being a fun learning experience. So okay, we've introduced the world matrix, so we're still working in device coordinates. So now it's time to set up the view and projection transformation as well. So you can't really tell the bounds of the scene here, but rest assured it's 3D. We can sort of see a perspective projection at play, whether we want to spin a triangle, plane, or again, sphere. So there we go. We just have a very involved world matrix. We're 10 units out of the scene, staring at the origin, and we've got a 3D projection with a 90-degree field of view. And again, you can play with it. You can change the clip planes, change the camera, maybe even make a first-person camera, depending on how deep you want to go. And students have a lot of fun playing with things like this, just, manipulating all the controls that define our 3D scene. And another thing that I find really helpful is in hardware accelerated graphics pipeline, at the end of the vertex shader, coordinates are expected to be in clip space, and the GPU manually performs the perspective divide. So that was always like a just trust me bro of graphics programming education, but now that we're writing from scratch, we have to do literally every phase of the graphics pipeline ourselves. So we perform our perspective divide once we're in clip space, and then we can fire off the familiar wireframe rendering draw call. So that just about covers vertex transformations. So now it's time to go ahead and render filled polygons. So we start off with barycentric coordinates, which looks kind of scary, but is actually the basis for pretty much all fragment shaders, because that's what's responsible for interpolating our vertex attributes across pixels. And I'll save the complete algorithm for the very end, but once we have that, if we feed in our positions, we can color based on world space positions, normals, texture coordinates, actually sample the texture given the coordinates, and then maybe even add some lighting with a funky coloring algorithm. And then so, right, we define whatever we like as a fragment input. We can say a fragment shader takes in a fragment input as well as uniform data, so that way we can conveniently supply some custom behavior to our draw mesh, which is basically our filled polygon rasterization algorithm. So here we're kind of just saying our input is our output. This one samples a texture, and this one does some cheap diffuse lighting. And then again, we've just got an array of function pointers, so just cycle them accordingly, and we get some cool dynamic behavior. So I guess this doesn't even need to be its own demo. It's really just calling this function pointer. But here is the final render. We get a photorealistic, Phong-shaded, real-time scene running at a reasonable 40 FPS. I lock the camera, so obviously this is very fill rate limited. So if we were to move our camera much closer to our head, our frame rate would tank, but this runs on like a medium power PC at a stable frame rate, at least good enough for learning. And again, depending on how crazy you want to go with optimization, maybe some next steps could be subdividing your screen with like quad tree and doing this with multi-threads, or you could even throw SIMD into the problem, but that's going pretty deep, at which point you should probably just start using the darn GPU. So that's it for the demos. So let's look at the actual draw mesh function. So I've commented it to basically map one-to-one to every stage of the hardware accelerated graphics pipeline, because the whole goal of this course is to be a precursor to hopping into OpenGL, so students have a better mental map of what's actually going on. They're not just memorizing the steps, which is kind of inevitable, right? This is a lot to absorb, but I like to think it just gives them that much better fundamentals. So we've got basically a fixed vertex shader. It's really just about fragment shaders for creating custom effects. We don't need to do anything crazy with like mesh skinning, so we can just have the same vertex shader. I group my vertex attributes into face, so positions, normals, texture coordinates. I transform these to world space, device coordinates, screen space. You know how all that works. So we can see just, world space positions, extracting the rotations from the world matrix and renormalizing them. No transformation on the texture coordinates. Perspective division to get device coordinates, remap to screen space. There's no notion of a viewport here. And there we go. So now this part is pretty awesome. It's basically what allows this to run in soft real time. So without this phase, if we were to try and render a triangle, we'd have to basically evaluate not only the pixels inside the triangle, but every single pixel in screen. So a very important optimization is our prepass, where we figure out the minimum and maximum of every triangle to create a bounding box, and then we'll do a point in triangle test for all pixels within our rectangle. So that way we're only evaluating all of these pixels, and the pixels I've colored orange will be discarded. So for all triangles, for every horizontal and vertical pixel in our triangle's rectangle, calculate our barycentric coordinates, which are effectively our point and triangle test. So if our barycentric coordinates lie outside of the triangle, we can go ahead and discard the pixel. Again, there's also some other little things like rejecting degenerate triangles, and this enforces backface culling. Again, I haven't gone crazy with rasterizer or just overall pipeline state. Same with the depth test here. We're doing a less than depth function. And finally, now that we have valid barycentric coordinates and we're shading the topmost pixel, we can go ahead and use those coordinates to interpolate our vertex attributes. So then we just feed them to our fragment shader, right to the frame buffer, and in about 400 lines of core renderer functionality, we have a filled polygon as well as wireframe capable software renderer. So for the demos, again, I like anonymous namespaces. It just alleviates a lot of busy work from separating between header and source files. You can see how I initialize the demos right there. They're just a bunch of function pointers. And then I've organized this engine into a bunch of scenes. Some of the code is kind of chaotic, but if you want to understand how this is being displayed to the screen, well, if we tunnel down the chain, we can see that rasterization scene inherits from a software rendering scene, so it overloads load, unload, and update. But my callback responsible for GP rendering is called onDraw, which of course the base scene overloads, which is really just an excuse to call present software image. So if you know OpenGL, you'll know exactly what this line does. We just allocate a GPU texture when the engine loads, and then whenever the software render is finished outputting into some CPU pixel memory, we just take it and apply it to a GPU texture and then sample it based on a full screen quad. So there you go. That's Graphics 2. Hope you enjoyed.